Okay, so I'm going to give you separate notes for this, but before we take a look at this notes, I kind of just want to get you to think through this. So what we're looking at is the area between two curves. So let's first just refresh your memory. How would I find my area underneath this curve? What do I do? You take the integral, and you integrate, and it gives you the area underneath that. So that would give us this area. Okay, now let's suppose that instead of wanting all of that area, I had another function. And I wanted to find, instead of all of the area underneath my right curve, just the area between the two curves. So instead of all that, I only want this area here. And let's just suppose that this is, let's say, from 1 to 8. And we'll just go ahead and call this f of x. We'll call this g of x. Okay. So instead of getting this entire area underneath, suppose I want only the area between those two curves. I want you to talk with your shoulder partner. How do you think we would do that? How would I get, instead of all the area, just that piece there? Go and take about 30 seconds, talk over your shoulder partner somewhere nearby.
I did originally do that. So eventually some
Okay, so what are your guys' thoughts? How can we find just that green area rather than our original, all that red area? What would we do? Subtract what? Good. So if we subtract our integrals, our red area would be all of this. I want to get rid of this area here. I don't want this area. So if I were to subtract this away, then I would be left with only my green area there. Oh, no, I don't want just that piece. Okay. Well, if we were to get rid of all of this, then we'd be left with just that chunk we want. So what we're doing here is that we would be subtracting those areas. So would you agree then that we would integrate the top one, our f of x? That would give us all of it. And we would subtract away from there the integral of my blue one here, g of x, which would take away what's underneath that. Are you guys in agreement with that? So that's going to be our basic idea for today. Now, of course, things can get a little crazy where sometimes it might switch which function is on top. So, for example, suppose they did something like this. They want the area between the curves, so they would want this area, and between there as well. They would probably stop there. Then we'd have to change which function's on top, but it still follows that same idea that we do with the area of the top function and subtract away from it the area of the bottom function. So I want to go and just take you through a few examples with this on Geometry Sketchpad, which better be good because I restarted my calculator or my computer for it. So here we've got our top function is 5 minus x squared, and our bottom function is going to be this x minus 1. And they will either give you the interval in which they want you to do this from, or you'll just use your intersection point. So if they want something other than just your intersection points, like if they wanted to also include over here, they would tell you that you would go all the way to, what's that, 3? But we're going to just go from our intersection points here. Okay. 22. Here we go. So that would be our area between the two curves. Now, so what you can see is this is our top function there. That distance or that height between them is going to be that top function minus the bottom function. So what we have is f of x is our top function that whole time minus g of x is our bottom function. We don't have to split up into those two integrals to set it up. Obviously, when we evaluate it, sometimes we might want to split up into the two integrals. Alright, so let's go and take a look at another example here. So here you can see it gets a little crazier where we have, starting out, our brown function's on top, and the blue is underneath, and then it switches. So you can see that it changed. Oh, right there. Okay, so here for this chunk, my f of x is on top, whereas my g of x is in the bottom. But for that first chunk, my g of x was on top, f of x is on the bottom. So it just simply means that we have to split up into two integrals. Our integral here would be g of x minus f of x, and then our integral here would be f of x minus g of x. So for our first chunk there, we have that. Are we only going from -1 to 0? I want all of it. Give me all of it. There. Okay, well. So what it's trying to say here, so what it's trying to say here is you can't just do one integral. So one integral can't find this area because it changes. So we'd have to do the two different integrals. Let's see if it does it in this one. Do I want this one? This one isn't very exciting. Okay, I thought there was a more exciting one. Maybe it's one of these ones down here. But so what we have again is that it's always top function minus that bottom function. And we're going to be going from those intersection points unless they specify otherwise. And as we saw with our second one here, if I were to find the area of each chunk here, I'd have to do one integral for this and then change my integral here, where it changes which functions on top, which functions on the bottom. So that's what we're going to be doing today. This is the starting point for what we end up doing over here. Okay, so this is really key that you understand this concept during that top minus bottom, because we will continue this concept throughout when we do our volumes, where we rotate these regions. Essentially what we're going to eventually get to, let me go back to our first one where it's a little less crazy, is that we're going to take this region and we will actually rotate it around a line and it'll make a 3D object for us. So the starting point for that is actually finding our area between the two curves. That will tell us our radius of that object, which we will use in a couple classes. So everything we've done so far is with respect to x, dx, which means that we are doing top function minus bottom function. So we're looking at our integral. Think Riemann sums those little rectangles are perpendicular to the x-axis. The height is going to be top function minus bottom function. But we are going to go a little bit into doing in terms of y. Where when we go to integrate our area, it is in terms of y. So we actually integrate with respect to y. Notice my functions, instead of being functions of x, they're functions of y. So we actually solve it x equals where it's in terms of y. And so then when we go to integrate, it's the area between your curve and the y-axis. So we would actually go, instead of top minus bottom, because we're no longer going top minus bottom, we're going to be going right minus left. Or you can think of it as, if you turn your head, this is top, that's bottom. So it's going to be right minus left. So it's the same concept, same idea. It's just now, instead of going with respect to our x-axis, we're going with respect to our y-axis. And so when we go with respect to our y-axis, it finds the area between your y-axis and the curve. Before, we were finding our area between the x-axis and the curve. So it's the same concept. It's just x-axis, it's top minus bottom. With our y, it's going to be right minus left. So still that same concept, but right minus left. Okay, so that's what we're going to be doing for our second concept today.
I have an extra.
Don't send on. Did it stop it when already?
Sure you did. No, this is what I think this is from way earlier. I think that's actually just an extra.
Okay. Right, is there one to connect these two? I'm sorry. I don't think there's first block of text is really just explaining what I was showing you with Geometry Sketchpad. Go ahead and you can ignore this limit notation, sigma notation. The integral is defined as the sum of all of our little integrals, or all of our little rectangles, that's all just the same. But don't let that scare you. We're not doing series and sequences like we did in Algebra 2. So just go ahead and take a look at these situations in which we have top minus bottom, and even though it might go underneath our graph, we're still going to do top minus bottom. So just going to take a look at that for a moment, and then we'll get going with this. Okay. Yes.
Do we have any grades for it yet?
We have play rates quiz and quiz one, but I don't think I've put those on SIS yet.
Okay.
So I have senior high six.
We don't put them out until you put the test. There's no venture.
Like it should have something on there.
Like, what is test? Yeah, like it's gonna use the test and because otherwise it's gonna. It's like right up
It's not the test, it's
Just put the water. I know. I'd rather just have nothing in there than have a bad grade.
Okay. So this will be on too. So even though we might have graphs that go underneath our x-axis, we're still going to do top minus bottom. Because if you think about it, our areas underneath the curve, or our areas underneath the x-axis end up being negative areas. So when we do top minus bottom, let's just suppose that our area here is negative 5. And let's suppose that this area is negative 12. Okay, so when we do top minus bottom, I would be doing my negative 5 area minus the negative 12. We end up adding that together, and that yields an overall positive result of 7. So it's still, even though we've gone underneath the x-axis, we don't have to switch which functions on top or bottom. We don't have to worry about the fact that those are negative, because when we subtract that negative, it adds the positive, and it takes care of that for us. So we will always stick with top minus bottom, top minus bottom, top minus y. Now when we go with respect to y, it's the same idea, just right minus left. Okay, so let's just go ahead and take a look at these first couple ones here. So here they specifically told us our graphs, but then they told us bounded by not just our graphs of y equals x squared plus x plus 2 and y equals negative x, but they also told us bounded by x equals 0, so that's going to be our vertical one here, and x equal to 1. So that is simply just to tell us what our bounds are for our integral that we're working with. Okay? So we're not, on our calculator, we're not going to be graphing what x equals 0 and x equals 1 factor 84s cannot handle that. That's just simply to tell us what our bounds are. If they didn't give us bounds, then we would be going on for forever and ever and ever because these don't, this doesn't intersect right there. Okay, so if there are intersection points, you're probably using those, but if they tell you bounds like this, then you're going to stick with that. Okay, I'm not sure why there's a 1 point Q, ignore that Q. Alright, so in these problems, these first two have the sketches already done for you, but you are most likely not going to be given a sketch, so you want to just kind of do a little sketch for yourself, just have an idea of what's going on, just so you can more easily identify your top minus bottom. I think it's a little easier if you go ahead and label these in terms of y1, y2. You can call it f of x, g of x. I think on the key they use f of x and g of x. On AP exam, you can call it whatever you want, just make sure you redefine it. But when you redefine it, it makes it a lot easier when you write out your integral. If I were to go ahead and redefine this and say y sub 1 is x squared plus x plus 2, and then I go ahead and let y sub 2, y sub 2 be negative x, then when I go to write out my integral, I can literally just say y sub 1 minus y sub 2. If you call it f of x and g of x, you can just say the integral of f of x minus g of x. So it makes it a little bit easier for you. I like to use y sub 1 and y sub 2 because if it were a calculator problem, then you can just correspond it with what you put it in your calculator as. Okay, so it's just a little trick for AP. You don't have to rewrite out this entire function if you redefine it or relabel it. But if you just said y minus y, that wouldn't be okay. There's two different y's there, so they need to know which one you're talking about. Okay, so we're just trying to find this area here. So this is my top. My top was actually y2. Oh, no, I just labeled y2 there. Whoops. Okay, my top was y sub 1. My bottom was y sub 2. So my integral, we're going from 0 to 1 of y sub 1 minus y sub 2. And we're still doing it with respect to x. And then we're going to go ahead and use our calculator a little more heavily for this, just to save on time. We can certainly do this one by hand. If I were to actually write out our integral here, this would be x squared plus x plus 2 minus, and always put these in parentheses just because a lot of times our functions have more than just one component, one term to it, and you want to make sure that you're subtracting that whole function, minus the negative x dx. So we could go through and actually integrate this by hand. And for your homework, I would recommend doing a few of them by hand, but I trust that at this point in the year, you know how to integrate. We've done it so much. So just to save on time, you are welcome to use your calculator, but I would recommend you still do some by hand just to keep refreshing your brain with that. Okay, so let's just go ahead and punch this into your calculator. Again, you don't have to graph this. You can just put it straight to your calculator on the home screen and type in your functions, or you can type your functions into y1, y2, and then on your home screen do y1 minus y2, kind of whichever you prefer. But go ahead and punch it in and see what you get. I did mine by hand, so let me figure out what the decimal value actually was. And again, as always, just go ahead and double check your answer with someone next to you. Okay, did you guys get like 3 1/3? Okay, perfect. So if you were to do it by hand, the exact value was 3 1/3. On calculator, I'm sure it's like 3.33. Now, we are talking about area, so technically this is units squared. I don't know that I've ever seen them expect you to do that on AP. Alright, so let's go and take a look at example 2. It says find the region bounded by those graphs, and then sketch it to integrate, must find the intersection. So here, they did not tell us from x equal to x equal, so we have to actually find those regions, or like those bounds. So we need to know then, we know that this is an upside down parabola, and obviously they've given us the graph here, but we know this is an upside down parabola and that this is a line. So we need to find these points of intersection. Now we are going to go ahead and do this without the calculator, because a lot of times they will make it without the calculator. But how do we find where two lines intersect by hand, not on the calculator? What do we have to do? Yeah, set them equal. So I'm simply looking to see where 6 minus x squared equals x. And then we're just going to go ahead and subtract our x over. I'm actually going to add my x squared over and subtract my 6. So we have x squared plus x, 6 equals 0. Let's put the factor. plus 3x minus 2. X equals negative 3, x equals 2. And that should look about right. So then those are going to be our x bounds for our integral. Now, once again, you can write this out without redefining them as y sub 1, y sub 2, or you can redefine them and then write out your integral. I'm going to go ahead and not redefine it just to kind of show you guys some variety with this. So I'm going from negative 3 to 2. Now my top function, I do like to write on my little sketch that I do like to go ahead and label which function's which, just so I'm less likely to mix these up. So this is my 6 minus x squared. This is my x. So my top function is 6 minus x squared minus my bottom function, which is just x. Yes. And again, we could integrate this by hand. And if you were to integrate it by hand, you would find the area is 20 and 5/6. I'm going to give that one to you. That's a free one. Alright, so my main concern today is just that we know how to do our setup. So I trust that you guys can do it. Do we have questions with those setups? Okay, so let's go and flip it over to the back side. So notice that now they start bringing in trig. So it says find the region bounded by the graphs x equal to 0 and the first intersection of sine and cosine. So that means that we're bounded by x equal to 0, our vertical line here. And then we have, which one's sine, which one's cosine? You guys don't have colors on yours, but is this top one sine or cosine? Cosine. And so we're back on here. So it says bounded by the graph of x equal to 0, and the first intersection of these two. So what we're trying to find then is this region. Alright, so I want you guys to go ahead and set up and integrate this one. I do want you to do this one by hand. So go ahead and set up your integral and then use the work off the side by hand. See what you get. You're going to do this one by hand. So my antiderivative of cosine is sine. My antiderivative of sine is negative cosine, so then minus the negative. Did you guys get root 2 minus 1? Good, I think that's what I got too. I mean, that's what I got up here, but I think that's what the correct answer is. Yes. Great, so root 2 minus 1. And as Chelsea was asking about, our antiderivative of cosine is sine. Our antiderivative of sine is negative cosine, so minus the negative is positive cosine. Good, okay. So, any questions with example 3? Okay, let's go ahead and take a look at, I just want to talk about example 4 real quick. So we've already kind of talked about this with our geometry sketchpad illustration, but we can see when it says find the region bounded by these curves, that's going to be this region, and it's also bounded by this region as well. So it's pretty much anytime these two curves kind of intersect to give us a chunk of area. So we can see here that it's going to change which integral or which function's on top. So we will need two different integrals. If I were to call this one y sub 1, and I'm going to call this one y sub 2. You should actually redefine it, y sub 1 equals this, y sub 2 equals this. But my first integral, this is my cubed function, so my y sub 1 is on top, my y sub 2 is on the bottom. But then for my next integral, my y sub 2 is on top, and my y sub 1 is on the bottom. So you would need two different integrals for that. How would I again find my intersection points here? What would I have to do? Yep, set them equal. You probably have to factor to solve them. But I want to go ahead and take a look at example 5. Because it starts to look a little crazy here. They've given us 3 graphs, and it says find the region bounded by our graphs. Y equals 12 minus x squared. Y equals negative x, and y equals 4x. So it's important that you know some information about your parent graphs in order to have an idea of which graph is which. But our 12 minus x squared, I'm going to call that y sub 1. That's going to be this upside down parabola here. Alright, so note this is y sub 1. And then I'm going to go to the next one, y sub 2. So y sub 2 is negative x. Okay, so that's going to be this guy here. Y sub 2. And then I'm going to go on the third one, y sub 3. So 4x. Okay, so when it says find the region bounded by these graphs, it's going to be the area that's enclosed by these 3 graphs. So what we're looking at then, and sometimes it gets a little crazy because it looks more complicated than actually is because these lines are intersecting in some of these spots. But what we have then is this region here we would include, right? It's bounded by all 3 of those. But wouldn't this region also be included because it's bounded by all 3 of those? And then again, this region's included because it's bounded by all 3 of those. Now I wouldn't include this, it's not bounded by that third graph. But essentially what we have is actually this continuous area here. So although at first glance it might seem that you actually have, let's see, 1, 2, 3 different areas, if you were to try to think of it that way, it would get pretty complicated where you have to split this one up because our top function is y1, bottom function is y sub 3. And then here for this chunk, we'd have to do top function is y2, bottom function y sub 3. But then we'd also have to split this up because my bottom changes here. And then we'd have to split this up. So that's actually, there's actually a much easier way to do it than doing those chunks there. Instead, just look at it as a whole. We know that we need this entire yellow area. So we only have to change integrals when it changes which function is on top or on bottom. So when I look here, would you agree it is the same function on top this entire time? Okay, so that doesn't cause us to change integrals. Let's take a look at what's on the bottom. Right, so here I have y sub 3 is on bottom. Now it does change which function's on bottom here. So at this point is when I'm going to need to change integrals. So I would actually have 2 integrals for this. My first integral would be, we would need to find this intersection point. But my first integral would be the top function is y sub 1. My bottom function is y sub 3. And I believe this changes at 0. Does it look like it's 0? Yeah, it does actually change at 0, 0. So here at 0, 0 is where we're changing. And we have to change integrals now because our bottom function changed. Okay, so then I'm going to add to this because I have one chunk of area. I want to add it to my other chunk of area. My top function is still y sub 1, but now my bottom function is y sub 2. Now, again, we have to find our intersection points, and those would be our bounds, but we know that 0 is that spot which is changing. So we didn't actually have 3 different chunks, we only had to do 2 different chunks. Because again, you only need to change integrals when it changes when what's on top or what's on bottom changes functions. Okay. I want to take a look at example 6 of how we set this up. So here it says find the region bounded by these graphs. Notice that our graphs are in terms of y now. It's solved x equals and x equals. So when we graph this, here's our 3 minus y squared. It's like a sideways parabola, half of the hyperbola. So I'm going to go ahead and redefine this as x sub 1 equals 3 minus y squared. And I'm going to call this one x sub 2 is y plus 1. Well, y plus 1 is just simply a line that's been shifted. So here's our x sub 2. Here's our x sub 1. If you struggle with how to graph these, you can always solve it for y equals, and then graph it, and that's going to be your line. So like, for example, over here, this is just simply the line y equals, what would that be? X minus 1. And you can see y-intercept negative 1, and then a 1 slope. So if you're not sure how to graph it in terms of y, you can always solve it back to be in terms of x. Here you would just have the 2 chunks, there'd be 2 square root curves that you'd be graphing. So that might help you out with graphing it if you're uncertain what's going on with it. Okay, so it says find the region bounded by these 2 curves. So what we're trying to find then would be this region in between them. And it's up to you whether you want to do it with respect to x or with respect to y. But sometimes it's advantageous to do one over the other. If I were to look at this here, if I were to do it with respect to x, then I would have, here's my top function, here's my bottom function for this region. But then notice now my top function has changed. And with this, I would have, this is my top function, this is my bottom function. And when we solve for this in terms of y, if I were to solve this for y, again, like I said, we would have square root. We have a positive and a negative. So your top function would be the positive square root, your bottom function would be the negative square root. So it would require 2 integrals, and it would require you to go and solve these in terms of y and both square roots. And integrating the square root might not be as easy as doing it the other way. If I were to do it with respect to y, so let's see what that would be respect. What's that? Well, if I do it with respect to y, so again, you can either think of it as turning your head so where it looks like this is on top, or just think right minus left. So when we go with respect to y, we do right minus left. When we do it with respect to x, it's top minus bottom. So when I go right minus left, notice it's the same function on the right the whole time, and then the same function on the left the whole time, so we could actually knock it out with one interval. So you could do it with respect to x, it's just going to be more work. If you do it with respect to y, it's less work. So you can actually choose either one for all of these problems. It's just usually one way is easier than the other. Okay, so for this then, if I were to do it with respect to y, so I'm going to go with respect to y, everything needs to be in terms of y. So I would do then my right function, so we're going to go right minus left when it's in terms of y. Again, when it's in terms of x, we do top minus bottom. Okay, so right minus left. My right function is x sub 1. My left function is x sub 2. I'm doing with respect to y. And so, because I'm doing with respect to y, I need my bounds to be in terms of y as well. So when I find my intersection here, let's go ahead and actually do that real quick. When I find my intersection for this, I'm going to sneak it in here. So I have 3 minus y squared equals y plus 1. So I'm going to probably have to factor here. I'm going to add my y squared over. So I have y squared plus y minus 2. Did I do that right? So that would factor into y plus 2, y minus 1. So I get intercepts of y equals negative 2 and y equals 1. Let's make sure that was right. Yeah. So y values. Negative 2 and positive 1. So when you go to integrate everything, if you're doing dy, everything needs to be in terms of y. If you're doing dx, everything needs to be in terms of x. Your function, your dx, dy, and your bounds. So here, my bounds then, instead of being my x values, because I'm going with respect to y, I need to be my y values. So I have from negative 2 to 1. So I'm going from this height to this height here. Okay. So when I go to do this by hand, what my integral is will be negative 2 to 1. My x of 1 equation was 3 minus y squared. And my x sub 2 equation was y plus 1. Again, always make sure that you put parentheses around it, because then we'd have to distribute out the negative. But this would be a lot easier to integrate to rather than doing the square root here. So notice, oh my goodness, we should say dy, we're doing everything in terms of y. So again, when you're doing dy, your functions need to be in terms of y, so it should be x equals, and your bounds need to be in terms of y. When we're doing everything in terms of x, your functions need to be in terms of x, so y equals, and then your bounds in terms of x. Integration techniques are still the same, just when we're integrating with respect to y, it's the area between the y-axis of the curve, whereas with respect to x, it's the area between the x-axis. Questions with that? So your homework for tonight is to finish these 2 packets. You probably got pretty far with your average value as it is. Now for the area between the 2 curves homework here, this box is just there for you to like draw a sketch of it. You don't have to always have like your 0, 0 set. You can draw however it fits best for you. And again, I think the key does f of x and g of x, totally up to you whether you use y simple or not. Any questions with what we need to have done for homework? No.